Hello everyone, it's February the 3rd. We're going to do February the 4th. So today we have two goals. Goal number one, of course, we're going to finish the daily challenge, which today we're going to do contiguous array, whatever that is. And the second, we are going to keep working on the question yesterday that we got stuck at. We got two methods and both got TLE. So I've been spending a whole day, not a whole day, like I have some moments that allow me to give this question a bit more thought. I didn't check the solution, didn't check the discussion because I really want to solve it by myself. So I had some thoughts, which I think I'm going to try later. But first, we have to take a look at this one, contiguous array. I don't remember doing this. Yes, this is completely new. So we're doing this a new one. Okay, which is good. Given array, it's a binary array, return the maximum length of a contiguous subarray with an equal number of 0 and 1s. So we want to return the maximum length of a contiguous subarray with an equal number of 0 and 1. So that will be 2 because that will be 2 as well. Again, it's contiguous, so the first thing in my mind is sliding window. So let's see if sliding window applies to this problem. So we're gonna have an array, we have some 0, 1s, right, whatever it is, and we are going to start the first one, okay, and then we'll look at the second one. If the first and the second one are 0 and 1, then we have a length of 2. And then we keep looking. What if we keep looking, we got more 1s than 0s? Then what do? Do we shrink? Well, we shouldn't shrink, right? Because if we shrink, and as we extend, I can give you a counterexample that we should not shrink. So maybe this is not sliding window. Sliding window seems to be a little bit iffy, right? Okay, if not sliding window, let's try DP. Okay, so something akin to Cardane. Let's say we have built up an array and we know the maximum length of a contiguous array with equal number of 0 and 1s ending at a certain value. Now, it is possible that it's 0, right? Like if the nums array, the length is 0, then the return value is 0. So at any value we're ending at it, so we compute the longest ending at a certain value, at a certain number, index. Now we'll consider the next index, right? So if we consider the next index, we look to the one before me, right? So the one before me will have the longest that's balanced, right? It's balanced. Then I cannot add myself, right? If I add myself, it will be unbalanced. So the longest that can include in me shall be the longest of the previous that miss a 0, right? That should be the longest that miss a 0. Hold on. Doesn't make any sense. No, we can count, right? So say the current value is 0, right? And then I have the previous value, I have the longest subarray ending at the previous one that is balanced. So we have already found that. That's ending at this one, okay? So now I'm at 0, right? So what I need to do is I need to go to my previous. We need to find the subarray, minimum subarray that has an imbalance of 0 and 1s, which means if I am 0, I need to find the 1, right? If this is a 1, then I have, no, hold on. So I need to find a subarray that has one more 1 than 0, right? If it's a 1, if 0 previous is a 1, then that's it. Then we can use the 1 in front of 1. The longest of that plus this, right? So if it's a 0, we're looking back, right? We're looking back one by one to find the first instance, right? The first instance where we have more 1s, one more 1 than 0. And then but this method, I mean, like, what if we don't find? What if we don't find? Well, if we don't find, that just means it's gonna be by myself, right? If it doesn't find, then it's just me gonna be by myself. There's nothing to balance. So like we find the first balanced one, and then we know this is from the balanced one to me. That is a contiguous array, right? That's a contiguous array. How can I find this one faster instead of going one by one? I'm pretty sure if we go one by one, we're going to time out because that is going to be O(n) squared, right? But what we want is not O(n) squared for sure. We want it to be faster. Given the length, I think we should look for O(n), right? We should look for O(n). How can we find the previous one faster? Well, if I am a 0, right? If I am a 0, I need to find the first one. Yes, I just need to find the first one, right? If I'm a 0, I just need to find the first one to my left. The first one I can find between that one and me, boom, booyah. That is, that range is balanced, and then we add the maximum of it before the first one, right? So all we need to find is the first one. And how do we find that index? We can use binary search. We definitely can use binary search. So all the ones, we have their indices in an array, or the zeros in an array. Whenever we find a 0, right? When I find a 0, and then what we need is to find the first one. So we use the index of the current 0. We throw that into the binary search. The binary search will give me the first one that's in front of me. Yeah, I can find the first one that's in front of me. And we just grab that, right? We just grab that. Can we find it without using binary search? Yes, we can. We can record the index of the previous one. So every time we hit a 0, we update the index of 0. Every time we hit index 1, we update index 1. So when I hit a 0, I have the previous index 1, right? I immediately get it. And if it's 1, I have the previous 0, and then I immediately get it as well. And if I have multiple zeros, then we just keep updating zeros, which is fine, right? Because what if we have like consecutive zeros, right? So for the 0, I get it. And now we have a next 0, right? And I say I need to find the first one. Now hold on, that's actually not right. Because if I find the first one, it doesn't guarantee how many zeros is in between. We do need binary search, right? So what I mean is, if I find my current 0, right? I find my current 0, and I want to know um, the first one that's in front of me, right? So now I need to find the first one that's in front of me. Once I find the first one that's in front of me, then I know how many zeros is between me and the first one, right? Therefore, hold on. I know the maximum length of the balanced array for the one in front of me, right? So I know that's a balanced. But I am a 0, right? Therefore, I need to find a balanced array. A balanced, well, a balanced array ending at me, right? That's what we want, a balanced array. If I can find a balanced array ending at me, nope. Equal number of a 0 and a 1, right? Which means, what does equal number means? That means if we have a length, the sum of this range shall be half of the size. Okay? We can use cumulative sum, so we can have the sum of anything. Okay? So I have up into me, right? I want to find hold on. I want to find the longest, as I'm still trying to do this, I found the longest that's ending in me. And I know the length, right? And I also know the sum, right? I know the two, but that doesn't help. It doesn't help. If I am a 0, hold on. So every single one, if I have the longest, right, which means I know this is the length and have the sum is half of the length, right? Now I have a 0 coming in. I cannot add the one in front of me because that will be imbalance, right? That will be imbalance. But if I'm a 0 and the one in front of me is 1, then I can get the maximum of this and plus 2. But why don't I do all the other combinations? Right? It could be other combinations. Doesn't seem right. Contiguous contiguous. Code number, hold on. If I have an example and I have a cumulative sum, okay? And then how about binary search? The longest lines, right? So we have minimum is 0, maximum will be the total length, and we get the middle, right? If we get the middle length, what do you mean? How do we evaluate if it's good or not? If we get the middle length, then we can search through the middle length, right? We can search through, see if it fits. What if it doesn't fit? Like, what do you mean by doesn't fit? Like this length, I find out, let's say, 2 little ones. And the next window, 2 little ones. Next window, 2 little ones. Still doesn't make sense, right? Because if it's 2 little ones, like some window I'll have 2 little ones, some window I have too many ones. And if it's too many ones, then we need to expand. If it's 2 little ones, we need to shrink. How about, how about divide and conquer? We split it into 2 halves, okay? Split into 2 halves. Let's say we get the maximum contiguous on the left and the maximum contiguous on the right. And then we need a crossing. Maximum contiguous crossing. Which I think it's possible. If it's a crossing, which is from the middle we go left. And from the middle we go right. Right? And as we go left, how do we know that it's balanced? Well, what we can do is, as we go, we record, right? We record, like if it's a 1, which is plus 1. If it's 0, we just now all we need is just the sum. Alright, so at each position we can have a sum. Okay. At each position I have a sum. Like position this, have a sum. On the right side it's the same thing. And then what we need to find is to mix and match. Or we can say if we count 1 with plus 1, we count 0 with minus 1. Okay? So at each position will be plus 1, plus 1, plus 2, and plus 1, something like that. So basically just the net, let's say net 1 count on the left and net 1 count at the right. Now these two should be adding together, should be 0. Right? Net 1 count on the left and net 1 count on the right, they shall be a 0. If they're 0, that means we shall have the same number of ones on the left and right. Okay, how do we find a match? So we have to go all the way down, right? We have to go all the way down and go right, we go all the way down, right? And then on the left, what we can do is find the longest for each value, right? From the longest, so it could be a dictionary, and so we find the longest for each value. Now on the right, every time we would extend, right? We extend and we need to find its reverse. So on the left, if we have, then we have one, then we keep searching, right? We keep searching, so we keep increasing, and now we have a crossing. Now we compare the two. So I think I can solve this in NlogN. Let's try it. NlogN. If NlogN I can solve it, which then it begs the question whether I can do this in Cardane. Oh, I forgot to do this for yesterday. All right, let's see if we can do this. Let's actually write today as folder 4. Okay, so here is my idea. We're gonna do divide and conquer. All right. So I'm gonna say def. Let's call it helper. So what do we need on helper? We don't need an index. We don't need an array. It's global. So we just need an index, a low and a high, right? So a low and a high. All right, low and a high. And what do we return? We just need to return the integer. Okay, we'll return the integer. Okay, so the base case is when low is equal to high, right? So we say if low is equal to high, that's the base case. That should return 0. There's only 1. There's no balance. It just returns 0. Otherwise, right? Otherwise we can say the crossing. We're gonna find the maximum crossing. So we say mid equals low plus high divided by 2, right? And then a crossing means to be from low, so we're gonna go to the left, right? Going to the left. So we're gonna say LD, right? Left dict is gonna be this, and then we're gonna say for I in range mid to low minus one, right? So it's mid to low, and every time nums I, if nums I, so we're gonna have a net 1 count, right? Net 1 count. Let's start with 0. If this, then net 1 count plus equal 1, else net 1 count minus equal 1, right? Once we're done, we just say LD net 1 count equals I, because we want to extend, right? If we have the same value, we want to extend. Okay. So after we go left, now we're gonna go right. So we're gonna say for J in range mid plus 1 to high, right? We'll also do net 1 count, right? So we'll do net 1 count. So we say if nums I is equal, if nums I, net 1 count plus equal 1, else net 1 count minus equal 1. Now here is, so we're gonna say max cross, right? Max cross length is 0. We don't know how long it's gonna be. So we're gonna say, now we have a net 1 count. We're gonna say if we're gonna say if minus net 1 count is in LD left dictionary, right? then these two, they match, right? So we can say max cross equal to max cross, and then it's going to be the j minus ld minus net one count, right? Net one count. Shall we plus 1? 0, 1, 2, 2 minus, yeah, plus 1. So that will be the max crossing array. Right, so once we're done, we have the max crossing, and then we just return return helper, the max of helper low and mid, helper mid plus 1 high, and the max crossing length. That's the helper, right? So when I return helper, low is going to be 0, high can be len, nums minus 1. Yep. Let's see if this one passing the base cases. So we have 0, 1, that should return 2, right? 0, 1, 0, that should return 2, and like 0, that should return 0, I'm pretty sure. There's no 1 option. And that's going to be nums. And this will be find maximum nums. Alright, we'll run this. That is pretty bad. That is pretty bad. How is this not working? Alright, do not panic. Let's just figure it out. Okay? Let's try this one. Let's see why it does not work. Right, let's say equal to 0. Okay, so coming in, mid 0, 1, mid is 0, right? Mid is 0, and then max crossing, 1 is from 0, so we take 0, right? We take 0, then minus 1, so a count will have minus 1, right? On this side we have minus 1. And on the right side, that kind of, so mid plus 1, which is here, right? To high, so 0, 1, to high plus 1. Still not right, but it should be high plus 1, right? It should be high plus 1. So mid, so we're going with 1. So 1 comes in, if this, so net 1 count becomes 1. And minus 1 is inside, right? So j is 0, 1. J is 1. 1 minus 1 shall be 0, because we set it to 0, right? It should be 0. 1 minus 1 should be 1. 1 plus 1 should be 2. Max cross should be 2. So return shall be 2. How is this not giving me the one I want? I do not know, but we can just probe at it. Let's print LD. Let's see what it looks like. Minus 1 is 0. That's exactly what we expect, right? And after this, let's check. Let's say print max cross length is 0. There is the issue, right? So let's say let's print net 1 count. Ooh, we didn't even hit here. Hold up. Ah, that's J. My bad. Yep. There we go. Small error. Yeah. Alright, let's try this. NlogN, I think it shall pass. Unless very stringent, right? So NlogN, it passed. So this is the same as the maximum crossing array, right? So this is like the maximum crossing array, which I seriously think we can do this. So this is very similar to the max crossing max subarray sum problem using the divide and conquer idea. The main logic is to compute the max crossing array that have the longest length of balanced zeros and ones, right? And the method I use is counting the net ones on the left and net ones on the right. That is +1 when encountering 1 and -1 when encountering 0. Then match the two. Then match the two net 1 count. So this apparently runs in Onlogn, and it barely passes with 4 seconds, right? So this 1 millisecond, it's not ranking. I highly suspect that a Cardane-ish method exists that can solve the problem in ON. So now let's try to see if we can do Cardane, right? Because it feels almost the same as a Cardane. So what do we do with Cardane? Well, I have this idea of 1 count, right? Maybe I can do that. The net 1 count. So what we want is the net 1 count to be 0, right? It could be larger than 0, which means we have more ones, or smaller than 0, which means we have more zeros. And what we want is to have it equal to 0. And we start with 0, right? We start with 0. So the first one, let's say it's become 0. I think about -1, or +1, right? So what do we want to keep track? What we want to keep track is don't know what we want to keep track of, honestly. Yeah, it's like we turn all the zeros into -1. Then the question is the longest subarray that add up to 0, right? The longest subarray that add up to 0. Which means if I'm looking at from my perspective, right, and I am a 1, so I want the longest, the previous that add up to -1. The longest that add up to -1. So a plus me, so that will be the longest that add up to 0. But I need something add up to -1, right? And probably also need something add up to 1. So for each one, I need 2 values. The longest that can add up to 1, and the longest that can add up to -1. And then, whatever my value is, I can get the longest that can reach 0, my current point. But how do I compute the longest that add up to -1? Right? Say I have my position, right? And then the position in front of me, I have the longest that add up to 1. And the longest add up to -1, right? I have these two. And I am at my position. And my position, let's say, I don't know, let's say my position is a 1. Then what? The longest. So what I need to do is I need to compute the longest that will be -1, including me, right? Well, think about it. If the previous thing carries 3 values, the longest that go to 0, the longest that go to 1, and the longest that go to -1, right? And on my current, if it's 1, then I already have leading to 1, so I just need to do the 0, right? And then the longest leading to 0, I have to. How do I compute the longest that leading to -1 from my perspective? Longest that leads to -1. Well, the longest that leads to -1. As I am 1, so I need a -2 in front of me. Right? I need a -2 in front of me. And how do I get to -2 in front of me? I mean, if the one in front of me, if they're all 1s, yeah, that seems convoluted. The longest that add up to 0. I mean, what I can get is the longest that add up to the, well, not the longest, the maximum. I can get the maximum, right? I can get the maximum sum ending at a position and the minimum sum ending at a position. That is something I can do. The maximum ending at this value. The minimum ending at this, so I have a maximum minimum, right? And I probably also get the maximum ending at this. And what does that mean, the maximum ending at this? Well, if it's the maximum, and I have an array, yeah, we can compute it. We can obtain the array, right, at each position. That is the longest. The longest that just can give me the maximum value. right? Give me the maximum value. So what does that do? I didn't do anything. I don't know. What's the I'm giving up. I have the O in login. Brute force definitely not one. Extra array. That's a win. Hash map. That's a win. Ah. Yeah, that's to add up to 0. How do we do this? Hold on. Minus 1 plus 1. That's minus 1, right? Hold on. That's an interesting idea. So if we count minus 1, minus 2, minus 1, minus 2, minus 3, minus 4, minus 3, minus 2. They never add up to 0, man. It never does. It's just, does add up to 0, but it's in the middle. So if we're looking at this, we say, what do we say? Minus 1, minus 2, minus 1. So the one we're looking at is like this. This is good, right? This is good. And from this one all the way to the end is good. So minus 1 and minus 2. Minus 1, minus 2. 0, 1, 2. Subarray between A, B. 2 and 4. 0, 1, 2, 3, 4. That is not right. It's 0. It's 1 and 2. It's 1 and 2, 2 and 3, right? 2 and 3. And of course these two, 0, 1, 2, 3, 4, 5. 5 and 6. 5 and 6. Yeah, we also have 5 and 6. if we encounter the same count twice, okay, that is the inside, right? So we keep counting, -1, -1, and then I +1, right? So I have -1, and I have +1. Yeah, -1 and +1, that's a 0, right? That's a 0, which means if we start at some point, and I reach the same position, then everything in between is good. So I start here, everything between, so 2 and 3 is good. 0, 1, 2, 2 and 3 is good. Oh, but no. It's a different. My thing is different. So I start with -1, and then we end at -1, so these two are good. And then -2, these two are good. Right? And then -3, so these two are good. -2 and -2, so everybody in between is good. Ah, that is pretty smart. That is pretty smart. Okay, so we produced this, and we can record their indices, right? We record their indices, and then we just this minus this. Now record the smallest and the largest index. We go min and max, right? Min and max. Well, if you think about it, the first time we encounter would always be the min, and the last time we encounter will always be the max. So the first time we encounter, we save it, and then every time we encounter, we just put in the second one. And also we compute. So every time we encounter it again, we can compute, and then we compute and we compute. Oh wow, this is pretty smart. So we are, I won't say we're not too far away, but honestly we are pretty far away. The key idea, right? So this one, I was close to. I had the idea. I had the idea of counting net ones, but I didn't realize that if we start this counting from the beginning, then anytime when two indices have the same count, that means the subarray in between has net count 1 equal to 0, which means it is a balanced array. Thus, all we need to do is to record the first occurrence of a certain count and compute the length of the balanced array when the same count occurs again. This is from solution 2 of the official answer. Alright, so what we do is what do you say net 1 count? Well, not net 1 count. Net 1 map. Okay. For I and in enumerate nums, and we have a rest shall equal to 0, right? We say if n, we need a rest and a count, right? So count will be 0 as well. So if n count plus equal 1, else I can probably write it like this: count plus equal 1 if n else -1, right? And then we say if count not in net1 map count will equal to I, right? Else res equals max res I minus net1 map count, and then return res. No good. Alright, so that's -1. And then that's +1. That's the 0. That doesn't look good. Why is this one is not working? 0 and 1. So we go -1, then +1 into 0. We get to 0. So we want to find, so whenever it's 0, right? Whenever it's 0, oh, so we need to consider the 0 case as well. So we say if count so it's not in, then we put zeros in, right? 0 equals this. And next time 0 comes out, well, because I'm doing this, right? So every time 0 comes out, so if count is 0, so it should be just if count is 0, then res equals max res and I plus 1, right? So that's just the 0 from the start to the current 0. Else, now we can just do aleph, this else. Yep. So special case, right? Special case where balanced array starts from the beginning, right? Special case. Balanced array starts at num0. And this, my friend, is ON. Yeah, I feel like my prowess is decreasing. Right? My ability is dropping. Yeah, that's ON. Shave off a lot of time. So this is ON, which have 1 0 1083. Second 44. All right. So we have another solution, I think. Another solution was called hash map. Okay, I feel like this is similar to what I'm doing, but yeah, that's the same. If I have count, when I minus get count. Oh, I put this. That is smart. That is very smart. Okay, so yeah. Yeah, this is smart. This is to avoid considering count equals 0 separately. Very smart. Then we don't have to do this, right? Then we just say if else, and it will pass. Yep. Yeah, that's very neat. I don't think it will be any faster. Oh, it could be because I don't have to do if statement. Yeah, that's fine. All right. Yes, that's a good problem, right? This is a good problem. Very good problem. All right, so we've done that. We're gonna back out this. Yeah, this stupid thing. So we need to check one thing. So sum nums I is smaller than 1,000, right? Which means the sum of everything. The sum of everything is from 0 to 1,000, which means the total is from minus 1,000 to 1,000. Therefore, we can build a hash map, right? So that's my idea. Is doing this is not working. So my idea is we build because the problem we have reduced the problem to the target, right? We want some, well, how many different type of combination and the sum will equal to the target, right? So, oh my god, I have to go back to this context. So the target, so we have a target, right? We have a target, and of course, so when we begin, we say we sort the array, right? We sort the array, and every time we're going to compare, right? So in the first one, I'll compare my value to the target. If my value is larger than target, we just keep going until the first one that's smaller than target, right? And then for that one, we're going to have the sum is just by itself, right? The sum is by itself, and that one has one count. And all the other sum from 1,000 to minus 1,000, so we have an array of 2,000 length. Everybody else is 0, right? Everybody else is 0. Okay. Now a new thing comes in, right? So that's the first one. And the second one, new thing comes in. Again, the new thing comes in, I say a target minus that. And we see how many we have, right? And then, well, we don't have any. So we add that one to it, right? We add that one to it, and then we try to add this to the next one, right? We add those. If it's too big, then we don't do it. If it's smaller, then we do it. Okay. Now the third one, right? For the third one, again, try to see if we have any. So if anything, we try to see if we have any. Now once we've done that, we need to add the previous ones, right? Which basically means we're going to search through the ones that's already in there. Yeah, we search the 2,000 things that's already in there. We search through them, and we find any that if I add it to them. So the idea is if there's some combination that's already existed there, right, it will cause it to become too big, then we just never record it, right? And we only do it to make sure that when we add it, it will be smaller, right? So we have to go through the entire list and find the ones that I can add and become smaller, so we add those. If we add it become bigger, then I don't add. And every single time I do it. Okay, let's try this. Who knows, right? Maybe this one will work, but I don't have high hope. All right, this is the third try. We need this. I need this. Cause edge case. So we need to handle the 0 cases. Okay. And now we do this. Div mod. S minus target. So we have the new target. And then this is 0. If target is 0. Wait, hold on. Did we solve this one already? One left shift I if target is 0. Hold a sec. This is S minus this, right? S minus this. So we handled all the zeros. S minus, so S minus so that's the target, say, the remaining non-zero values, right? The non-zero values. The non-zero values need to add up to something. And if the non-zero values is, oh, I see. Yep. If target is 0, which means they have to be taken all of them, then it's just a 0. Okay, so these are all fine. This is just all the edge cases you have to handle. Honestly, maybe we can. Nah, 0 is nasty. 0 is nasty. So we just get rid of the 0. So remaining is just from I to the n. Right? From I to the n. Okay. So from I to the n, what I need is a dictionary. New nums. Okay, so we have a new nums. Yes. Now I need a dictionary, which is the count of sum. I'll call it sum count, right? Let's call it sum count is going to equal to a dictionary. Better yet, I can use a default dict for this. Yeah, I guess it's fine if it's not in there. Yeah, let's use a default dict. So from collections, import default dict, right? So I use a default dict for this one. All right, that's gonna be an integer. So what do we do? We're gonna go from the back to the front, right? We're gonna say for j in range, where is back? Oh, back is n minus 1, right? And I go to I minus 1, n minus 1, okay? And for every single thing, right? For every single thing, we're gonna check, right? Check for what? Go through the dictionary, right? Well, we first see if it's in there. We say if target minus, now I have to say if target is larger equal to, if target is larger or equal to nums j. Right, if it's smaller, then we just keep going. So on the first one, I do think we need to say sum count 0 equal 1, right? Sum count 0 equal to 1, because if I find a 0, I want to add it, right? I want to add it. And then we just say res Well, plus equal to sum count dot get target minus target minus nums j. Right? If it doesn't exist, it's going to be 0. Oh, that's fine because it's a counter. If it doesn't exist, it'll become 0. Now after that, right? After that, actually, I don't want these to pollute, right? If it's not in there, I don't want to pollute. So no, I actually don't want to be a dictionary. I just want it to be a regular dictionary. So if target larger than, right? Then they'll get 0. Perfect. And after that, we're gonna say for count in sum count, right? Count in sum count. So if res plus count, what is equal to? Do we have 0 in this? We do have 0 in this. But we handle the zeros already. Zeros are handled differently. So if I am the target, then nobody can add to me, so there's no point in putting me in. So if this is smaller, right? If the result plus count, what the hell is that? For count in this, not result. I don't know what I was doing. So for count in this count, right? We say if nums j plus, it's not count. It's the sum for s in this, right? Plus s, if that is smaller than target, has to be smaller than target, then sum count if it's smaller than this, then we say if this thing plus s is not in sum count this equals 0, and then sum count this plus equal 1, right? It's only if it's smaller then we do this. And once we're done, then we go back to the front. The next target, we add how many that we can get from it, and then we expand. And once we're done, we do this. Let me see. Is this gonna work? Dictionary change size during iteration. Yeah, it does change size. So we probably say dot keys. That probably also, yeah, I cannot do this. So we need to list this. We pass sum, and oopsie doozy, we only get 71. All right, so there's something wrong. Let me think. This is correct, right? If target minus the current number, which means something we have in there, hold on. We have some values add up is this. Some other value add up is this. Some other value add up is this. And then, and I can add up to this whole thing, right? I can add up to this whole thing. Let me just, they all become negative, right? They all become negative. And then it will work. I feel like the problem is the repetition. But I handle the repetition. Oh, I think I know. If this plus this is smaller than target, right? So this s is the previous one we have, and I can add to it, right? Now, if this thing, if some count s has multiple counts, right? Then when I say this plus this, it shouldn't be one, it should be multiple. It shall be some count s. Are we too big? Are we too big? It's not some count s. Maybe we need to create a new sum count every single time. That's the old sum count. I need to put into the new sum count. It could be like if I, as I'm doing, right? Because I'm looking at nums j. For nums j plus some sum, and then it increases some count or something else. And then when I handle that, we'll add the change the value. That could be the reason. So in that case, what should I do? Well. What we should do is that's going to take time if you want to merge two dictionaries. Like, take a copy of one of them. Okay, so what you saying? What I'm saying is rest plus filter. Now I'm gonna do new ones. So what I'm saying is if we have a temp, let's say equal to sum count. How do I copy? Like this? Copy a dictionary. It's fine. It's all integer, so we can do a shallow copy. It's fine. Oh, I have a dot copy. Okay. I'll use dot copy. Sum this dot copy. Okay. So I copy it, and now I can say for sing sum count because I'm not gonna change sum count, right? So about this, if this was this, and then this is gonna be temp. So, and then this will be temp. This plus equal to this, right? And when we're done, we say sum count equals temp. Run this. Now we pass. Now we pass. Okay. And this one, definitely we can do this. Save a line. New nums. Why do we have new nums? I never use new nums. Right? I never use new nums. Alright, let's see. Come on. Be gentle with me. Be gentle with me. Let's see how this one does. Alright, so 670 something, right? Oh, I think this time we might have it. Wow, this is just special. This is special. We went from time limit exceeded to freaking 76 milliseconds and 99%. The power of thinking a problem over. All right. Wow. I have been stuck with this problem for, I was stuck yesterday night, right? I was stuck yesterday night. Let's say it's 0202. Right? I started yesterday night, got 2 TLE, and was frustrated. Today, which is this day, I thought it over and had a new idea, which is as follows. I had a new idea. Now the basic logic is the same, right? It's the same. We want to find the number of combinations of nums that can add up to s minus target 2. Of course, before we can do this, we must clear out the edge cases, which include the existence of a 0, which must be considered separately, because we can always add plus or minus to 0 and not change the outcome. 2, if s minus target is not an even number, then it is not possible to find a not possible to create an expression to sum up to target. All right. I'm thinking maybe this one is not necessary. Yeah, but anyway. So we have a 3, right? A 3. If target, if s minus target divided by 2 is equal to 0, which means all of the non-zero numbers must be taken to make the expression possible. And then the answer is just the complete permutation. And the answer has nothing to do. And then the answer with the non-zero elements is 1. So after the edge cases, we can create a hash map which records the number of occurrences, right, for all valid sum of any combination of numbers. We go from largest number to smallest, thus any time a sum of combination, right? Sum of combination exceeds the target, exceeds this, we don't count it. And to find the number of combinations that satisfies this, it is the same as 2sum, same as the method in 2sum. Runtime, I don't know the runtime. This one grows however it grows. But we have a 76 millisecond. That's very fast. Alright, I kind of want to just stop here. So we're gonna make like a trilogy series of this. Like tomorrow we're gonna look at the solution. Yeah, I actually want to do that. Tomorrow we'll look at the solution. And I'll probably do an easy one tomorrow. Yeah, this problem requires more, because I think it's important. It's important to know how to find k-sum. This is basically a k-sum problem, right? It's a k-sum problem. But I'm happy that I got it done. Yeah, we'll wait for tomorrow. We'll do exact same thing one more time, 3 days in a row, 3 times the charm. I think it's important. All right, that will be it for today. I will see you guys tomorrow. Adios. Hasta luego.